Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are having the compiler design subject. So we are having the parsers, that is two types of parsers. One is the top-down parser and another one is the bottom-up parsers. And in the top-down parser we have studied recursive descent parser, and another one is the predictive parser, the tabular version of the recursive descent parser, where the stack is controlled by the program itself. Whereas in the case of bottom-up parsers, we have studied once again two types. One is the shift-reduce parsing, and another one is the operator precedence parsing. The shift-reduce parser is working by constructing the rightmost derivation in reverse, and there is a process being held called handle pruning. Then, whereas in the case of operator precedence parser, we have studied that there is an exclusive type of grammar needed, which is nothing but the operator precedence grammar. And then we will be constructing the precedence relation from the operator precedence grammar, and the relation will be actually there are three types of relations. One is the less than, another one is equal, and another one is the greater than. Less than is denoting the left end of the handle, which is supposed to be that is shifted onto the stack, and equal denotes we are somewhere in the middle of the handle, which requires still further shifting towards the stack to find out the entire handle. And whereas greater than denotes we are on the rightmost end of the handle, so which requires the next action to be carried out as a reduce action. So if you don't find any valid relation, then we will go for that is declaring some error saying that the input is not valid as per the specification of the language of the grammar. So that is about the operator precedence parsing. So here we are having a class of an efficient bottom-up parsers called LR parsers. So the LR parser actually they are the type of bottom-up parsers, and they are scanning the input from left to right and constructing the rightmost derivation in reverse. So every bottom-up parser is going to be that is constructing only the rightmost derivation, whereas in the case of top-down parsers they are constructing the leftmost derivation. In the case of LR parsers, so they are more efficient, and the first L stands for left to right scanning of the that is input, and the R stands for the rightmost derivation being used for parsing. And the speciality about the LR parser is it is capable of constructing parser for almost there is all the programming languages. So it is you can write grammar means we will be able to definitely come up with an efficient parser. So that is the reason why LR parsers are more familiar in the case of the programming scenario. And when you talk about the structure of the LR parser, we are having a driver routine and a parsing table, which is going to be constructed with the help of the given grammar. And by using the parsing table and the input also along with the stack, we will be parsing the string. So that is what going to happen as far as the parsing process is concerned. So here is the structure of the LR parser. So we have a table generator software. So there is a program, and what will be given as input for that table generator is the grammar, and the table generator will generate the parsing table. So soon we will be studying the structure of the parsing table, but later. And once the parsing table has been constructed, then that is going to be part of the LR parser, and now we are having the parsing process. So where there is an input being given as given for parsing, and it will produce some output, and in the meantime it is being in use of there is a use of a stack for parsing. So, if the parsing table has been already constructed with the help of a table generator program for the given grammar, then we need to identify what is the input for which the that is parsing is to be done. So, we all know that the output of any driver, the parsing of whether it is going to be LR parser or shift reduce there is bottom up parsers or top down parsers, the output is going to be a parse tree. So, when you are giving the input which is to be parsed, so if the input is completely valid as per the specification of the grammar given, the output that is going to be a parse tree will be generated as output. But in the meantime, the parsing is that is using a stack. The stack is going to have some grammar symbol which will be that is moved that is from the that is a parsing action. So, normally we will be having a state number followed by the grammar symbol, and always on the top of the stack we will be having a state number. So, those things we shall study, that is when you are studying the parsing table here. So, this is what the general structure for any parser, but in the case of the LR parser also almost equivalent, and we know that there is an input being used, the stack is being used, both will be that is needed by the there is a LR parser, and output will be produced provided you are having completely a valid input as that is input is given. So, now what is the need that is what is the reason for the attractiveness of LR parsing? The first is it is capable of constructing that is LR parsers for all programming language constructs. So, if you can write a context free grammar, then certainly it is possible to come up with the LR parsers for that grammar. So, that is the first reason why there is your LR parsing is more that is familiar, and the next is it is going to be very much equivalent to the shift reduce parsing, as we find that the possible actions are going to be shift and reduce most of the time, and finally it will be going for an accept or it can even be an error provided there is no valid movement as far as that particular configuration is concerned. And another important reason for the familiarity of the LR parser is the there is way in which it is detecting the syntax errors. So, LR parsers they can detect syntactic errors as soon as it is possible to do. So, there is it makes the or it is identifying the errors as much fast as possible. So, that is what your LR parsers are that is more familiar. So, now when you are looking at the complexity of the LR parsers, so we find that the table construction is not very easy. We have already studied predictive parsers and even the shift reduce parsing, operator precedence parsing also. So, everywhere we find that the parsing table construction or the rightmost derivation construction or the precedence relation construction, so they are not much complicated, but whereas in the case of LR parsers, constructing the parsing table is going to be a very difficult job. Moreover, the parsing table is going to be quite larger in size than compared with the precedence relation table in the operator precedence parser or the predictive parsing table as far as your predictive parser is concerned. But here we are making use of a specialized LR parser generator that is taking the context free grammar as input and automatically producing the parser for that grammar. Parser I mean the parsing table. And suppose if you find that there are ambiguities available in the grammar, then the parser generator is capable of locating the constructs where the ambiguities are being generated, and it will ask for additional information from the grammar writer, that is whoever is trying to construct the parsing table, so that we can provide the additional information. For example, if you are taking the there is a arithmetic expression grammar, you can even construct a parsing table for the that is the ambiguous grammar, but provided we give more information to the LR parser generator about the that is your precedence, associativity, all those information if they are given, then we can say that the parsing table construction is going to be possible even for ambiguous grammars. So, there will be provisions. For example, one of the familiar parser generator is YARC, that is your yet another compiler which can construct the parsing table or can construct the parser from the that is grammar specification. So, if you find that the grammar is completely unambiguous, and then there is no need of giving extra information for the parser generator to come up with a deterministic parsing table. Whereas, in the case of the grammar has some kind of ambiguity, then we must go for that is providing additional information to the parser generator, like who gets the higher priority and who gets lower priority, and what about the associativity of the operators, and all these things can be provided to the parser generator just in the procedural format, so that the parser generator can take care of the parsing process or the parsing table construction without any there is ambiguity. So, this is about the difficulties, and even you can take this as an advantage, that is the speciality about the LR parsers, because they are capable of handling even the that is ambiguous grammars for constructing the parsing table. So, now we can see that is what are going the techniques going to be used for the parsing table construction. So, LR parser is going to be a very broad class of parsers, and so we see that there is a parsing table being used as far as the specification of the parser is concerned, and the parsing table is going to have the same structure, but whereas how do we come up with the parsing table? To come up with the parsing table, we have three methods. So, one is going to be the simple LR method, we call it as SLR, and another one is the canonical LR, we always call it as CLR, and the final one is going to be LALR, or we can call it as look ahead, that is LR parser. These are only the three methods used for constructing the that is parsing table. So, as you can see that the simple LR parser is going to be the one with there is the very simple procedure for constructing the parsing table, whereas in the case of canonical LR parser, the method being used for constructing the parsing table is quite complex, and moreover the parsing table which we are obtaining for the that is obtaining for the grammar with the help of the canonical LR parsing table construction process is also going to be quite larger. Whereas in the case of your LALR parser, it is having the intermediate power in between that is SLR and canonical LR. So, we are seeing that the simple LR is having that is it is very simple, but the drawback with that simple LR is it may fail to produce a parsing table for some grammars, which means that there are grammars, even though they are not ambiguous, the SLR parser, because of the simplest procedure being followed for constructing the SLR parser, it may fail to produce the parsing table. So, whereas in the case of canonical LR parser, it is going to be the most powerful one, and because of the most powerful parser it is, we can say that the class of the grammars being used for the canonical LR parsing table construction will be high. That means, if we can come up with a context free grammar, certainly we will be able to generate a canonical LR parsing table. But the problem is it is very hard to implement, and another thing is the size of the parsing table is going to be very large when you are comparing to the size of the parsing table for the same grammar being produced by an SLR parser. It will be even double or even more than that when you are comparing your SLR and CLR. The advantage of SLR is it is much simpler, but whereas the advantage of your canonical LR is it is completely reliable, saying that given a that is grammar, definitely we will be able to come up with the that is your parsing table. But if you want to come up with an intermediate power, then we can go for LALR. So, it is having the power in between your SLR and CLR, but the most familiar that is your parsing LR parsing generator is YARC, that is nothing but yet another compiler, and which is actually using your LR that is LALR parsing table. So, we shall see the that is a parsing process and the that is a structure of the configuration and those things, but after a short break. Welcome back. We have seen the three methods being used for constructing the LR parsing tables. One is the simple LR, and the next one is canonical LR, and the last one is going to be the LALR. As I stated earlier, SLR is the most simplest one, but it may fail to produce valid parsing table for some of the grammars. But whereas your CLR is the most complex one, and it is capable of producing valid parsing table for any grammar, provided it is a context free grammar. And when you look at the that is LALR parser, that is your look ahead LR parser, it has the intermediate power in between the CLR and the SLR, and also the familiar LR parser generator is using only this LALR parsing method. And another point to remember is the number of states in the finite automata constructed by the SLR parsing table is going to be lesser, but whereas CLR it is going to be very large. But LALR, as it is doing a process called merging of states obtained from your CLR, that is items. So the number of states available in your LALR parsing table is also going to be less when you are comparing with CLR. So that is the reason why we call it as the LALR parsing table is having the intermediate power in between both SLR and CLR. So that is about the three techniques being used for the LALR parsing table. And now let us see the that is the structure of the LR parsing table. So generally parsing table is going to be the table which is having rows and columns, and we have already seen one parsing table in the case of predictive parsing. So predictive parser is using table for parsing this string, and the table is constructed from the grammar with the help of two sets. One is called the first set and another one is called the follow set, and the rows are actually indexed by the variables and the columns are indexed by the terminals. Similarly, we have used one table called precedence table, which is being used by the operator precedence grammar, operator precedence parsing, and the table being used by the operator precedence parsing is also indexed by that is row wise index as terminals and even column wise index as terminals. And what we have in the table is like the relations, it can be either less than or equal or greater than, but if relations are not found, then it means that the particular that is point denotes some kind of error being detected. But whereas in the case of LR parsers, so the tables are not very easy. So we have two important components. One you can, as you can see, that one is going to be the action component, and another one is going to be the go to component. Both, that is action component and go to component, are actually that is indexed by row wise indexed by the state numbers, and whereas in the case of the columns are concerned, in the action component the columns are indexed by terminals, whereas in the go to component the columns are indexed by the various variables available in the grammar. So that is what the structure of the that is LR parser. We have action and go to, and this table structure is going to be common for all the three types of LR parsers, whether it is going to be SLR or canonical LR or LALR, it is going to be common. And what will be the role of the driver routine here? So it determines that is the current state which is on top of the stack called that is SM, and whatever is going to be the current input symbol, that is I, which is there in the buffer, and then after that it will carry out the action. So what are the possible actions? So it is going to consult the action for SM of m comma ai, where SM is the current state on top of the stack and A is the current input symbol, and there are four possible actions which can be there in the that is your LR parsing table. One is going to be the shifting, and another one is reduce, third one is accept, and the last one is going to be error. So shifting is actually the yes, shift yes. It means that if shift the current input symbol onto the stack and continue from the state called yes. So that's the meaning of the shift yes. Shift the current input symbol from the buffer to the stack and then resume the parsing from the state called yes. Whereas in the case of reduce is concerned, we find that beta is going to be the handle on top of the stack, and this beta is going to be now replaced by A. So, remove everything from the stack, which is nothing but the beta, and now we go for pushing A onto the stack. So, that is about reduce, and accept, it will go for declaring that the parsing tree has been completely successfully constructed, and this error telling that when there is no possible shift, or it is not possible to go for a reduce action, or otherwise we can't even accept, then it will be going to be an error. And whereas in the case of go to function, it takes a state and a grammar symbol as arguments. The grammar symbol here we mean it is going to be a variable. So, if both are given as inputs and producing a state as the output. So, two inputs for the go to function, the state number and the variable name, and producing a state as the output. So, that is what the parsing table structure. And when you look at the parsing table, that is configuration. So, the configuration of an LR parser is actually defined as the two components. One is going to be whatever is on the entire stack, and the other one is whatever is on the entire buffer. So, the stack is normally having the combination of the grammar symbols, whereas the buffer is going to have only the terminal symbols from the input. So, if you combine these two as a pair, then we will be calling it as the configuration of the LR parser. So, as we proceed with the parsing, so there will be some change be happening in the that is either on the stack or on the buffer or on both. So, they keep on changing the configuration, and at the end of the parsing process, we will go for a configuration which will be the accepting configuration, saying that the parsing input has been accepted. So, if you are not able to reach that particular configuration, then we can declare errors saying that the parsing has been failed. So, the components are, we can see that there is a state called S0, that is starting state of the entire recognition process, then followed by a grammar symbol called x1, then once again we have another state called S2, S1, then x2, S2, and finally it is going to be xm and sm. So, what do we find here is this always there is a state called some sm or sn on top of the stack, and every grammar symbol is separated by two states or bounded by two states. So, for example, if I am taking that as S1, X2, S2, we are going to recognize X2 or any pattern recognizable from X2, but start from state number S1 and go up to the state number that is S2. And whereas in the case of here, that is we are having Sm-1, Xm and Sm, you recognize a pattern from Xm, but starting from Sm-1 and go up to that is Sm. But whereas what do we have in the buffer? So, it is called the unexpended input. It means the input which is not so far recognized. So, this configuration is telling you that we have processed the symbols from A0 to that is AI-1, and what do we have here is X1 to Xm. So, if you combine these two together, actually we will be having the sequential form. So, this configuration is actually representing the sequential form. There is x1, x2, x3, etc. up to xm, followed by ai, that is ai plus 1, ai plus 2, etc. up to that is going to be an. So, this is what the sequential form, and the sequential form it says that it is going to be a rightmost derivation actually. So, if it is going to be a rightmost derivation, we all know that from right to left, if we are scanning, we will find a variable, and that variable is going to be further expanded. In this case, if x is going to be a variable, and this variable is going to be further expanded. So, this is what your the configuration of your LR parser. So, we have seen that there are two number of that is components, whereas in the case of LR parser's configuration, we have the stack and another one is going to be the buffer. The stack symbols which are having states as well as the grammar symbols from the given grammar, and every grammar symbol is separated by a pair of states, and whereas in the case of remaining unexpanded input is concerned, we will be having all the symbols in the order which are yet to be that is parsed. and if you combine these, we will be having the sentential form, which will be actually representing the ith sentential form. We will be getting after processing I number of or I minus 1 number of symbols from the input. So, this configuration, if you want to say that it is going to be the initial configuration is the one where we will be having only the start state on the stack and the entire input on the buffer. So, for example, if the start state is going to be S0, so that will be on the stack, and the string to be processed is going to be A1, A2, A3 etc. up to AN, then the pair is going to be S0 on the stack and A1, A2, A3 etc. up to AM on the buffer, saying that this is going to be initial configuration. And finally, what is going to be the final configuration? So, we will be having some that is state, like, or we will be having the start symbol of the grammar on the stack, and there is nothing else as far as the buffer. So, that is going to be the accepting configuration. So, if you start with the starting configuration and after changing or updating the configuration in various stages as per the parsing table entries available in the given parsing table. So, if you are able to reach the final configuration, which means start symbol is on the stack and there is nothing on the buffer, we can claim that it is going to be the final configuration. So, once we have reached the final configuration, we can say that the string has been accepted. Actually, all these entries available in the that is the configuration or the stack or pointers to the parse tree, because every parser is supposed to construct a parse tree as output, provided the input is going to be a valid one. Even in the case of LR parser also, we need to construct a parse tree for the given sentence. So, if the sentence is valid one, the parse tree is to be constructed. So, here as far as this case is concerned, the configuration, the first part of the configuration is the stack, and every entry available in the stack except the states, I mean the grammar symbols available in the that is the stack component are all pointers to a node in the parse tree. Finally, we will be having only the start symbol available on the stack, which means it is going to be a pointer to the start symbol of the grammar. The start symbol of the grammar in any valid parse tree must be the root. So, we will be having the start symbol on the root, that is nothing but the pointer to the root of the entire parse tree. So, if in this context, if you find nothing is there in the buffer, this parse tree is the valid one. If you find that there are still more number of symbols on the that is your buffer, it is not a valid configuration, or sometimes we may not be able to that is reach the start symbol of the grammar even after processing all the grammar symbols, that is all the input symbols from the buffer. So, that is also going to be another erroneous configuration. So, that is about the configuration of your that is the LR parser. So, to summarize, we have seen that is what is going to be the structure of the LR parser and what is the LR parsing table structure, and finally, we have seen that is what is the that is configuration of an LR parser. So, a parsing process is starting with the initial configuration and going up to the final configuration. As far as the question components are concerned, so the structure of the LR parser is going to be the one, and the parsing table also, what is going to be the structure of the parsing table, and there are three methods already we have studied, what are going to be the methods for constructing the LR parsing tables, like the SLR, canonical LR and LALR, and even the configuration, how the configuration changes, and to mark the progress in the that is your parsing process. These are the question components, and with this I complete this episode. Thank you all.